Let's start with some very basic rules so that we can find antiderivatives of some more advanced examples. So first of all, we should, right, the first derivative that we looked at was a power rule. So let's do the same thing for antiderivatives. Remember, the derivative of x to the n was multiply x by the old power and then subtract 1 from the power. So sort of the opposite of that is to divide x by the new power and then add 1 to the old power. So certainly the antiderivative of x to the n is x to the n plus 1 over n plus 1 plus some constant of integration c, as long as n is not negative 1, right? If n is negative 1, then we get a 0 on the denominator, and that's no good. How do I know this is right? Well, if I differentiate this thing, I should get this thing. What happens when I differentiate x to the n plus 1 times 1 over n plus 1? Well, you bring the n plus 1 down in front. That n plus 1 will cancel with this one, and then subtract 1 from the power, and you just get n. So the derivative of this thing is actually x to the n. So that's how we check that the antiderivative we got is correct. If you're asked to compute an antiderivative, write down the answer, and then if you want to know if your answer is correct, take the derivative of your answer and see that you got the thing that you started with. Okay, so the same linearity rules that applied for derivatives, limits, sigma notation, all of those things still apply to for antiderivatives. So let me let capital F and capital G be antiderivatives of functions f and g. The antiderivative of the sum is the same thing as the sum of the antiderivatives plus c. The antiderivative of a constant multiple is the same thing as the constant multiple times the antiderivative plus c. So now that we've got those things, let's look at a few examples. By the way, what happens if n is equal to negative 1? Off to the side here. So, for example, what's the antiderivative of 1 over x? Can you think of a function whose derivative is 1 over x? Well, if you remember your rules for differentiation, we know that the opposite derivative or the antiderivative of 1 over x is natural log of the absolute value of x plus c. Because when I differentiate this thing, I'm going to get this thing. So here's the special case, right? This power rule works for all of the n's not equal to negative 1. Here's the rule for when n is equal to negative 1. What about this thing? What's the integral of sine of x dx, or the antiderivative? Well, I need to think of a function whose derivative is sine. Cosine is pretty close. If I take the derivative of cosine, I get negative sine, but we want to get positive sine. So the antiderivative of sine is actually negative cosine. So this is negative cosine of x, and then we want to tack on the constant of integration, right, plus c. Okay, so in order to do antiderivatives properly, you really need to have a firm grasp of your table of derivatives. All right, so here's our first example of a typical function, right? It's got a trig part and it's got some algebraic part, almost a polynomial anyway. So we want to find the antiderivative, or the same thing as the indefinite integral of the function 4 cosine x plus 2x to the 5th minus square root x all over x dx. So that tells us that we're integrating with respect to the variable x. Like when we take a derivative, we need to know which variable we are taking the derivative with respect to which variable we are taking the derivative. Okay, so we know that antiderivatives go through scalar multiples and sums, We don't know what they do with fractions, so maybe it's a good idea to rewrite this thing as a difference. So 2x to the fifth over x is the same thing as 2x to the fourth. And then x to the 1/2 divided by x is the same thing as 1 over x to the 1/2 in the bottom, which is the same thing as x to the negative 1/2 written in the numerator. So make sure you're good on how we got from here to here. That's just algebra. Okay. Now to take the antiderivative of this sum and difference means we can just take the antiderivative of each individual piece. And now to take the antiderivative of 4 cosine of x, I need to think of a function that when I differentiate it, I'm going to get cosine. Well, I know the derivative of sine is cosine, and so the antiderivative or the indefinite integral of 4 cosine x, that's just going to be 4 sine x. What about this thing? Well, the antiderivative of x to the fourth, we know we add 1 to the power and divide by the new power. So don't worry about the 2 for now. So the antiderivative of this thing is x to the fifth over 5. And now multiply that by 2. So x to the fifth over 5 multiplied by 2 is just 2/5 x to the fifth. What about this thing? Bring down the negative, right? X to the negative 1/2, I'm going to add 1 to the power and divide by the new power. So when I add 1 to negative 1/2, I get positive 1/2. And to divide by positive 1/2 is the same thing as to multiply by positive 2. So minus positive 2 x to the 1/2, and then just make sure to tack on the constant of integration c. All right, for one more example, we know when we take the antiderivative, so for example, the antiderivative of 2x was the parabola x squared plus some constant c. And so c could be anything. So c is just the whole family of parabolas, right? So x squared plus 1 raises the parabola up 1 unit. X squared plus 2 raises it up 2 units, so on and so forth. So if I give you an initial condition, then that will determine which one of the curves from the family of curves I should take. So in this example, we want to find f of x if we know that the initial condition, f of 0 is equal to negative 2, and we know that f prime is equal to e to the x plus 20 over 1 plus x squared. So we want to do the same thing as before, only in the end, we want to actually find what c is. That's the only difference. So if I know that f prime is equal to this thing, then I know that f of x, right, the antiderivative will undo the derivative. So I know that f of x is the antiderivative of this thing. Well, what is the antiderivative of e to the x? Well, I need to think of a function whose derivative is e to the x. That's just e to the x. So here I'm going to get e to the x. And now 20 times 1 over 1 plus x squared. I need to think of a function whose derivative is 1 over 1 plus x squared. That's tangent inverse. So the antiderivative of e to the x plus 20 over 1 plus x squared is just e to the x plus 20 tangent inverse of x plus some constant of integration c. Now, here's the general antiderivative. This thing tells me I'm looking for a particular solution. So I know when I plug 0 into this thing, I'm going to get negative 2. So when I plug 0 into this function, I'm going to get negative 2. So I take the function and plug in 0 everywhere I see an x and set that equal to negative 2. I know e to the 0 is 1. I know that tangent inverse of 0 is just 0. So I get negative 2 is equal to 1 plus 0 plus c. That is, negative 2 is equal to 1 plus c. That tells me that c is equal to negative 3. And so the function I'm looking for, right, it's just this thing, only replace c with negative 3. So actually I could just do this. So minus 3, and this would be a good final answer for a particular solution, right? This is a function whose derivative is e to the x plus 20 over 1 plus x squared. And when I plug in 0 into this function, I'm going to get a negative 2.